Questions, questions, questions.
I have a question. Arkadiusz, when did you start first being interested in quantum physics?
I think it was like probably I was 15 or 14, and I have a brother that is 15 years older than I am, and he was at that time he was studying electronics. So he was bringing all kinds of electronic devices home, and of course I was playing and destroying them, and that was fun for me and problem for him. And I remember once, quite, it was like, I don't know, late 50s probably, and he came home and he learned somewhere about chain reaction. You know, nuclear chain reaction, that what is in the bomb, right? And he was telling everybody, and I was present, how this chain reaction works, like these neutrons multiply and multiply and multiply, and in no time at all the universe explodes because it's chain. You know, one neutron causes some other neutrons to hit other neutrons and so on, and the universe gets destroyed. And it was something for me. My goodness, that's something. Oh. And I remember, and until this day, you know, that this idea of the chain, you know, like. And the universe getting destroyed, and I said, "Oh my goodness, I want to learn, not to destroy the universe, of course, but I wanted to understand what it is. What are these neutrons? What are these things, the little things that you don't see, and they can destroy everything. You know, make a bomb, and the bomb can destroy not only the Earth but the whole planetary system." That I got interested in something very, very small, invisible. I didn't know yet that it was like has anything to do with quantum physics. So that was the first thing. And then the next was when I was already in the gymnasium or lyceum, how you call it, right? I was reading a lot of popular science literature. And I remember there was one very good popular book written by American George Gamow, was his name. It was translated in Polish, and there was about uncertainty relation in particular. And I remember the picture, you know, how it is in the quantum world. There was a man with a gun and trying to shoot a tiger, right? Like that, yeah? But the tiger was not just one tiger. The tiger was everywhere, because uncertainty principle means, you know, that you cannot really, if you want to ascertain the position, okay, the momentum got starts to be uncertain, and so the tiger moves. So you can't shoot the quantum tiger because it will never stay in place. And I said, oh my goodness, this quantum world is so interesting because nothing is certain. I want to learn about this. And that was probably the beginning. And then, of course, I was reading other popular science journals. So little by little, I got interested in two things, in the big things like the structure of the universe, how the whole universe is being built, what is the shape of the universe, and how to, and of course, I was reading a lot of science fiction books. So there were these travels, you know, light years. Light years. What are these light years? And okay, so I wanted to, of course, to travel faster than light. So that is how it all came. But until it was time to decide what I want to study, I was not very sure whether I want to be an engineer, like my brother, and construct things. But I was not very good with construction. My construction never lasted, even when I was building little planes from wood and paper and so on. They were not. I was not very happy. They always crashed. Okay, so I was not very good with engineering. So finally, I decided at last moment that rather I want to do some thinking than building. That's.
So, Ark, when you finally chose to go into physics, when you went to university, did you find that the understanding you had from popular physics and the things you would read as a youth, did you find that your understanding changed as you actually became a physicist, or did you have a good foundation from those things that you had read?
I think this is the same for everybody. I mean, you start learning something, you go to university, and you start with learning all kinds of tools. And in physics, they are in particular mathematical tools. So they are tools and tools and tools, and you learn tools, and almost. So it's like learning techniques, how to do it, what to do it, and then of course, yes, you have to study disciplines, but there are textbook disciplines, and they never answer the questions that you want to have answers, right? Mm-hmm. It's. You have to do problems, okay? You have to do some experiments. I was very bad with experiments, you know. I had to go through the physics laboratory, right? So there were these standard experiments, like measuring, I don't know, gravitational constant, or measuring electric charge, okay? Standard experiment. And whenever I was doing experiments, the result of my experiment were always contrary to what textbooks were telling me. So I had to learn how to cheat. Okay, that was the cheating consisted. I knew what should be the final answer. Okay. I knew that my results, the measurement results, would never give this answer. So how to tweak the measurement results so that at the end you would, but they should give the answer, but not too good, right? Because then then you would get the bad note because it was put clear that you cheated, right? So, but even if you cheated, to understand how it works, you know, you were learning the machinery of but still, I think I may have discovered great things, new that no one ever measured, you see, and maybe I discovered new particles or something like that. But I was just a student, so okay, I learned how to cheat, and that was. That was good, yeah. But no, the university studies did not satisfy me at all. So I said, okay, after a while, I started working on my PhD. My PhD, it was also like, you know, difficult work, give you some satisfaction, but it was not, I wanted to know how to build a time machine, how to travel faster than light, how to explain telepathy and such things. I was always interested in these things, and I was always far away from these things. And now, right now, I had the feeling that I am still far away from these things, but maybe closer, right? I know the difficulties, but it's always looking forward and trying to do more and more and more.
But your university studies were still a pretty good foundation in order to learn quantum physics, right?
Not really. No. The point was that I had one very good or two very good professors who, when I was asking questions, they were able to answer, "We don't know." And it's great, when a student asks professor a question and the answer is, "We don't know." It's not yet known. Okay, that was great to have because it needs some courage from the professor, right? To professor would like to always answer, "Oh, it's well known. It's well known. You have to study this, read this, read this, read this, read this, read this." But if you learn that something is not known, okay, that's for me, right? Yeah.
Do you think something has been lost in the field in terms of such bigger questions or like the unknown? I just asking because I recently read Werner Heisenberg's autobiography, Physics and Beyond, and it's really fascinating because they spent like days and hours discussing philosophical questions and speculating, and they were really like fascinated about the big questions. But it doesn't sound like that what you described now from your experience at the university.
I think this problem of big questions, it has been lost. When I am today, when I read books from like recently, I was reading several books on philosophy of physics by Arthur Eddington. Eddington was the Englishman, and he was writing these books on philosophy of physics like in 1930, 1935, 37, just before the Second World War. And there were these big problems of quantum theory and theory of gravitation, and he was he understood the problems in both. Okay, in fact, he was one of the scientists who helped to verify Einstein theory of gravitation, how the light rays bend in gravity field during eclipse, sun eclipse. Okay, so when I read people by Heisenberg, okay, when I read even Einstein, when I read Eddington, they are deeply thinking people, and this kind of deep thinking, I think, disappeared with time. And nowadays, of course, we have popular books about multiverses and parallel universes and going faster than light, but they are not, they are somehow bound to the contemporary theories which are based on fashion and on money rather than pure interest how the universe is working. I lack this independence of thinking of the old time. You see, complete independence and thinking deeply. I don't find it in the popular books that I read today. No. Something changed. And probably for me it changes when the, I mean, in these older times, the universities were independent units, okay? Like a king, there was a king or there was someone in the university, and it was independent from the rest. And professor, once he was hired, he was independent thinker. And of course, locally, it was clear for people locally who were paying the money whether they want to support this professor or not, okay? And today, money comes from multinational organizations, and these people, they know nothing about persons who they give money to, except okay, what kind of grant application? And you can study books how to write a grant application, okay? So you write a grant application so that you are assured that it will be given, and you lose sincerity and you lose depth. You just want to get money, right? It doesn't matter. And once you write this grant application, you get money. You started to get, oh my goodness, now I have to be sure that the money that was given will be justified. So I cannot discover something strange because it will not be approved. I have to do something that will be considered as a progress in what is fashionable now. So it's very bad now, you know.
So Max Planck wouldn't have happened in today's world.
Oh no, Max Planck wouldn't have happened. No. Yeah. Yes. Max Planck, Schrödinger, all these great people, and Einstein wouldn't happen. No.
If you had to describe one person, one researcher, for example, when you were younger or more recently, that really had an impact on your studies, on your line of research, who would that be?
Oh, I think it would be my PhD advisor. I came to him when I was fired from little university in a little town, and I was fired not because of scientific reason, but because I couldn't stand the gossip of a little university, you know. So I protested, and so I got fired, okay? Because I was not following the everybody path. So I came back to my old university, came to a professor that came just from Princeton, brought a wonderful new car, and so I was impressed, and I said, I want to do PhD. Okay. I want you to be my advisor. Okay. Can you give me a subject? Oh, if I have a subject, I work on it myself, you know. I will not give you, you invent your subject, okay? So he gave me I was completely free to choose my subject. And but on the other hand, when I had some idea, he said, oh, good, work for it. He didn't even have to understand, you know, work for it. It's great. So it worked for me. I don't know if it would work for everybody. I mean, for the PhD students, I was supposed to write my PhD in 4 years, right? After 3 years, I had nothing, not even slightest idea what I am. I was trying this and this and this and this and this, and I got finally I got really scared that I will not make it. But at some point, I was like an international conference, and organized it in the mountains in southern Poland. I went there as a student, and it was a very nice international conference because after lectures there was a bar where everybody was collecting, right? And we were drinking beer and wines and whiskey and whatever else, right? All these great people, professors and whoever else, and I was a little student, so I was with my glass, right? I come to one expert and I ask him question, and the answer is, "Oh no, very interesting question. You should work on it." So I came home from this conference and I said, "Oh my goodness! So there are questions that, so let me work on it." And in 2 weeks, I had my PhD ready.
In 2 weeks?
In 2 weeks, right. I mean, there was this question that was, I knew that nobody knows answer. So I thought, okay, let me look at it. So I look at it, read, papers. Oh yeah, that's interesting. Well, let me play. So I played, and after 2 weeks, I go to my professor. I had it. Oh, then you publish it. Okay, I had no idea what it means to publish a paper, right? But essentially, so I published 2 papers, and bah, I had my PhD.
What was the topic of your PhD?
Oh, okay. So it was this story. Okay, when this my PhD advisor came from US, from Princeton University, okay, he was there collaborating with the American by the name Arthur Whiteman, and Whiteman was one of the inventors of what is called axiomatic quantum field theory. Now, there is a word quantum, okay, so we know it has to do something with quantum. Then it's called field theory. Field means, in this case, means like electromagnetic field or field of particles like electrons. Okay, so it's a quantum field, and it's theory is clear theory, but it's axiomatic. Means that it's mathematically precise. Because physics, theoretical physics, is almost never mathematically precise, okay? Physics has their own way of calculating, and they don't care much about rules, okay? Whether something is allowed or not allowed. In mathematics, we have like a problem of taking limits. Like if you try to add 1 + 1 + 1 + 1 and infinitely many times, you get infinity, right? So physicists quite often get infinity, and they don't like infinity, so they invent, oh, maybe we have to cut not so infinitely many, and they invent ad hoc rules so that finally they get finite answer. And some people say it's cheating, and physicists, well, cheating, but you got the right answer. It agrees with experiment, so there must be something in this cheat. It's cheating. It's up to you to discover, how to make this cheating works. Okay, you see, this cheating works, and you get the right answer, and it agrees with experiment, and it predicts results that agree with experiment. So there must be something in this cheating. It's for the mathematician to find out how to fix it. It's not for us. We are specialists of cheating, right? It's a clever cheating. So now I like this mathematical, and I like fixing, and I didn't like cheating. So I consider myself, okay, I want to do everything precise, and I will really be mad at every cheating that is being done. And so it came. So the subject of the thesis was related to quantum field theory, but this time it was also mathematically precise. but it was called algebraic. So algebraic because I like algebra. You know, algebra it comes from Arabic words, and these Arabs, they invented algebra, and I like algebra. So that was yes. I think then also when I was doing my PhD, I was kind of fascinated by antimatter, because I could see in the subject of my thesis antimatter floating around. And today also I am interested in antimatter and how antimatter, what happens to antimatter? Why our universe is full of matter and antimatter has to be, I think there should be symmetry. Where this is antimatter universe, and I don't know where it is. But what we know that if antimatter universe would collide with our universe, there would be big explosion, and matter and antimatter would disappear, and light would appear. Well, maybe it will happen. I don't know.
Well, Ark, you mentioned that back then compared to now, the university was a freer place because you could do what you want and you knew who you were getting your money from. Were there any problems in Poland, or what was the relationship between the university and the government in Poland at the time?
That okay. That was Poland was a communist country, but and Russia was a communist country, but all the science was really on a very high level. So the Western scientists didn't mind coming to Moscow and visiting Russian scientists. Russian scientists were not allowed to go essentially abroad, but they could invite, and there was no problem with understanding each other and with international collaboration between West and East. And Poland was relatively free. There was much more freedom in Poland than it was like in Russia on the east or in East Germany on the west of Poland. So when Russian scientists were coming to our conferences in Poland, that was for them something great, because first of all, there was more freedom in Poland, and second, they could meet the Western scientists who were coming to Poland, because Poland was it was for them easier, right? So that was one thing. Second, the universities, even if so the main the whole power was in the Communist Party, at the level of the universities, where it came to such disciplines as physics or mathematics, we had no real interference from there. So that was first thing. And second thing, there was one wonderful thing, because we could buy all science book, which Russians were translated, almost everything what was published in the West were translating into Russian. And then they printed it and make it available for no money at all. So me being a student in Poland, I could afford to have a library of 1,000 of books translated from English to Russian. I was buying from pennies, for pennies, right? So I had all these books, and that was something like never before or after. I mean, that was, for me, it was really what helped me to do things. And within the university, we had complete freedom of traveling, almost complete freedom, right? Okay, when I want to travel abroad, I needed a passport. I didn't have my passport. The university had a passport. Or even not the university, the police had a passport. They were keeping passport. So whenever you wanted to go abroad, you had to go and talk. Okay, you were not free to go abroad. Okay? You have to talk. And they talk, why do you go on abroad? And so on. If you were good as a scientist, no problem. But if you were, they will make it difficult and they say, okay, you have to collaborate with us. So that was, these were the stories, but they didn't affect me really, except that, of course, I had my advance, like when to become professor, I had delayed it by several years because I didn't agree with the politics. So, but nothing serious.
Well, I have another question.
Yes.
Can you, if it's not too complicated, tell us what you're working on nowadays?
Oh.
Something to pique our curiosity.
Yes. Okay, with this work, it's like that. I have dreams. Okay, I have dreams. What I really would like to do, say, build time machine, or understand antimatter, or explain poltergeist phenomena. Okay. These are my dreams, or somehow fix quantum theory and merge it with theory of gravity and build a unified field theory. Okay, they are dreams. But of course, I have these dreams, but then I see stairs that I have to climb, and these stairs are, okay, the first thing is that I don't understand, for instance, what are spinors. Now, spinors, you don't know what are spinors, but how to say, every little particle, they kind of is whirling around, spinning, right? And physicists can measure, and there is something like elementary spin, and it's related to what we call Planck constant. Okay, that's this elementary. So these particles are spinning, but no one has an idea how they are spinning, because if you try to build a model of a sphere that is spinning, or something that is spinning, you find that to have the properties that this particle have, this thing would have to spin faster than light, so it would explode. So we know something is spinning, but we had no idea, is it really spinning in our space, or in other space, or we need more dimensions, because it's not the usual spin. Okay, so I want to understand spin. I want to understand spin, and to understand spin, okay, it's related to some algebras, and then there's this story that you are getting emails, right? They help you to do your research, and they prevent you. For instance, I got email this spring, I think. Oh, there is this conference about Clifford algebra. It will be in August, international conference, and Clifford algebras are related to spin. So I said, okay, you are invited to present a talk. So, okay, the conference will be in China. Well, there is this, what is called COVID, right? So there is no conference in China, of course. So it will be online conference. Okay, I agree. So I signed for the conference. Then in August there is this conference, so I prepare a talk, and of course I write what I would like to do, as it would be already done. It has already been done. Okay, I give a talk for 30 minutes, but now I have to write a paper, and I have a deadline till the end of December to write a paper that would prove that what I was talking during these 30 minutes is really good stuff and true. Okay, and explain. So of course, in this talk of 30 minutes, I put on my dreams. That I would like to prove or to show or to develop, but now it's time to make these dreams come true, right? So I mean, and it takes months. Okay. So suppose that I am now working on this algebra to finish to be on time with this paper. Okay. Of course, I know it's technical, it's just tools, so I'm wasting time, but nevertheless, I'm supposed to be an expert physicist, so I should be able to do it in no time at all. So I am working to make it work. Right? So, okay, but after that, I will have next thing. I want to know whether antimatter, whether it falls down or goes up. No one knows, you see. There is this question whether antimatter falls down like matter in gravity, for instance, field, right? Or that it is repelled. It would be nice if it is repelled. You could build, spaceship, right, with antimatter. It would be repelled by gravity, of Earth, navigate in this strange way. And no one knows how it is. Experiments were supposed to be done in the 50s already, but until now, experiment doesn't tell us how it is. So the theory, I don't know why. I am suspicious. I am, fan of conspiracy theories. So I think there is something there they are preventing to discover these properties of antimatter. They know it of course, but now that's why these experiments are delayed, and now 70 years and still we don't know the answer. No, it's impossible. But I will discover it through theory, not from experiment, but through theory. So that is my next project. Okay, it's how antimatter behaves in gravity fields, which should lead me to what I call the unified field theory, which is something that Einstein somehow tried several times in different versions, and according to some, there was a Philadelphia experiment when there was a teleportation and travel in space in time, and but then it was all hidden and made secret. Anyway, I want to build this unified field theory that will help us to achieve time travel and seeing through closed walls and such things, everything. Yeah, but that will come next.
Well, that's always pretty fascinating, but well, at least from my perspective, all these problems are so unsolvable for a simple mind of normal people. I mean, what motivates you to do this kind of job?
Oh, essentially, what motivates me is that when you have a hammer, right? You go around and see what can you hit with the hammer. I know all this mathematics that should be can be used to build everything. So I am going around and what can I do with this mathematics? I know. Now the point is that of course, if you nowadays we have this internet and everybody is publishing online all kinds of things. So you can go around, and there are hundreds of people that claim they have unified field theory, or they discovered all theory of everything and so on. And then they know how to explain paranormal, and then you start reading this paper and you see how much disinformation there is, and how much nonsense is being published, and how much nonsense is being published also in prestigious journals, because people don't have really time to read. They are busy with producing things. So, and it took me a while to understand that there is a lot of noise, and I want to produce something that is not a noise, right? So whether I will be able to do it or not, I don't know, but at least you try to do something that will last and that is true. And it's for God to decide whether you discover something or not, or for goddess, because there was this Indian mathematician, right? Ramanujan, right? And he was self-taught, and he was a genius, and he was claiming that it was a goddess that was telling him the formulas, and so he was producing stuff that was absolutely good, and no one knows how he got these ideas. And later mathematicians found that he was right. Yeah? He was having help from some other dimension. So I think if I work hard, if I am good, good boy, some goddess will help me, yes, and finally I will be able to do something with my dream. I want to be able to time travel. And not only me, I mean, I want you also to be able to time travel. I mean, not too far, dangerous time there are these prehistoric times. No. But just a little when it is needed. Yes. So, and we'll see what happens.
I've got a question about time travel, Ark, because I've read a few things, a few bits and pieces where you've written about time travel. And one of the things that I think you've said, but I may not have understood it correctly, is that there will probably be certain types of time travel that aren't possible because of the logical contradictions that might come into play. So I wonder if you could tell us how you picture a possible type of time travel, and maybe if you have any, and what do you think when you see movies about time travel or read science fiction about time travel? Do you think they do a good job, or do you think it's just kind of entertainment and they have too many logical contradictions?
No, the logical contradiction, the most well known is, of course, you go back to you time travel back and you kill your grandfather, right? So of course there's no chance you will be born, right? And yet, so it's a logical contradiction. Huh? You are here, you exist, you go back, and you make yourself not to exist, right? So we have this contradiction. Now, so what is, and of course you can invent, as you can imagine, many similar situations that would cause a logical problem, right? But on the other hand, forget about time travel. Like we are here when we think we have a free will. We think we can choose this or that or that or that. But we cannot choose everything. Okay, we can do certain things, you know, sometimes very little. Sometimes when I think about this free business, to what extent I am free, I think that the only control that I really have that is not pure mechanical, I can have control over my thoughts, some control over my thoughts. Thoughts are not material, okay? I have, of course, I do not have full control of my thoughts, right? Because if something happens, I start thinking about what happened, right? But when I am relaxed and so on, and when I need to make a decision, I have some control of my thought. But I do not have free will in the sense that I can do everything, you know? Like I cannot jump higher than 1 meter or something like that, yeah, even if I want. Huh? So there are restrictions. So I think it will be something similar with time travel, that yes, we will be able to time travel to some extent and in a certain way, and we will have certain freedom of observing things maybe, and maybe even doing something that is allowed. There will be things that we can do, like move something, some stone, right? It will not cause any contradiction or so. But when it comes to serious changes in the history, we will have may have the problems, and we may have been in danger even trying to do such things if we go. Okay, so that's how so that's one thing. Second is that this time travel, it has probably to do something with quantum phenomena, that is with uncertainties. That is, you want to go to some place, but there is no guarantee that you will go to this place. You may end up in a completely different place that you wanted to go, right? Mm-hmm. And then instead of, you can get stuck in a wall, like in this Philadelphia experiment, right? When you start reading, yeah. So there will be danger and there will be uncertainties, and so there will be manuals of time travel. You have to learn manuals, because otherwise, if you don't read the manuals, and if you do not follow the instruction closely, you instead of doing time travel, you will cause something happen, you know, and bad things will happen. Now, concerning, but I think it should be possible at least to go there as observers first. Okay, you can observe. Second thing, you will be never able to prove that you were there, because it may cause a contradiction. Okay, you were there, you observe things, you come back, and now you tell stories, right? And someone said, okay, bring me something from this, go again and bring me the stone that you have seen with this hieroglyph. You can't do it because it would be a proof, you know. It's like with paranormal phenomena, okay? We have all kinds of millions of observations, but if it comes to 100% sure proof that there is such a thing, you find there will always be a possibility that it's happened by accident or by something, you know, or you were dreaming instead of doing things. Okay, so there are things, and I think time travel belongs to this category, that you can do things, but you will not be able to prove that you time traveled. You don't have to, of course, like with intuitions of paranormal phenomena. Okay, you have precognition, you follow the precognition, you avoid crash, for instance, right? Because you and then you tell someone that, oh, I had this precognition. Oh, how many people have precognitions and things happen, didn't happen, okay, so you cannot prove. You use it successfully, you know, for your goodness, but it's not, I think one day will come when science will be able to deal with such phenomena that are not repeatable and have no proofs. But right now, science needs mostly needs repeatability and proofs, right? Of course, not always. Like there is no proof that Big Bang ever happened, right? And everybody accepts it. And you cannot repeat it, right? The science, okay? So there are things even that in contemporary science that are not repeatable. There are no proofs, but everybody takes it for a while as truth, right? But I'm thinking about science of what is consciousness, what is information, what is non-material world. This is still in the future. We don't have methods.
I have a question. A few years ago, you published a book, Quantum Fractals from Heisenberg's Uncertainty to Barnsley's Fractality.
Oh, yeah. Oh, this book, yeah. Yeah, I had a dream. Okay. Probably for more than 10 years, I was working on trying to improve quantum theory, because quantum theory is known that you can calculate things, but you don't really explain anything. You know how to calculate. Shut up and calculate. That's what you are being told, and don't ask questions. You know? So I was trying to fix it and build an alternative that would explain how things happen, and in particular how what we call collapse, quantum collapse happens when the wave functions suddenly make jumps, and like when electron goes from one orbit to another orbit, we know it's not true, it's not really the case, but something happens, something jumps, and now we are told that it's not an electron that jumps, it's some probability cloud, whatever it is, that changes instantly shape. So I was trying to build a model, how it happens. And after I did it, of course, it was very unrealistic model, but it still was working. Unrealistic in the sense that I demanded to the universe to be a supercomputer, computing in no times at all, impossible number of bits and so on, and we don't know where is this computer in the universe, right? We don't see computer in the universe. We see things, atoms, but we don't see computers. So anyhow, so I was happy with this theory, and then I tried to look what this theory would tell us about this Heisenberg uncertainty principle, which was telling us that it is impossible to measure at the same time, for instance, position and momentum, according to some books. And in my theory, the theory that I developed, it was clearly possible not only measure simultaneously position and momentum, but measure many other things simultaneously. And the question was, what happens when you start to measure things that normal quantum theory tells you it's impossible? So I started to ask this question: what happens if you do what standard textbook tells you you will never be able to do, and you should not even try? So I developed this theory. And in particular, what happens when you when you measure simultaneously many things, they start to behave in a chaotic way, but in a chaotic way that is at the same time organized into fractal. Because fractals, how you produce fractals? Fractals on a computer, you produce using random number generators. So you produce a lot of, this is one way of producing fractals. There are other ways. But so I started to play with it. And finally it came a book telling what beautiful structures may come out when you start doing what contemporary quantum theory tells you should not do. And now what I see is that experiment gets closer and closer, and I think in 50 years or 100 years from now, experimentalists will be able to do the experiments that I was describing in these books, and they will find these fractals, but it will take 50 or 100 years. So for now, it's a mathematically correct science fiction. This my quantum fractal business. Yeah. One day in the future, it will be on everybody in every textbook, but not before 50 years.
Did you get any feedback for your book from the scientific community?
Oh, very small feedback, probably like, I don't know, 10 or 15 quotes. But what happened recently, I thought I will put my book on academia and start a discussion of this subject. So I wrote to the publisher, please, can I make this book available for discussion on Academia Edu? And because when people discuss books, they will try, when they are happy with the discussion, you will get even more buyers, you know, because people get in. So it was just last week. I got a reply, oh no, we would be happy to have another book from you, but please, your book is still being sold and we are getting, so no, we will not allow you to make it publicly available, right? So the book is apparently being sold, not being quoted, and I am invited to write another book. So probably if the book would not be such a success, they would not invite me to write another book about anything else. So that's the story.
I've got a question about something you said about those fractals. You said that they are the patterns that you get when you do these multiple measurements are chaotic but organized. So I wonder, is there a similarity between that and, let's say, you were talking about probability clouds, like in a particle, where it seems to me that is that a similar example, because there's a chaotic element of where a particle is going to be in a certain cloud, but there's an organized element in that cloud itself will have a particular shape, like when you see electron orbitals. Is that a similar concept?
In a sense, yes, it is similar. Now, the point is that there are two things that happen. One is we have this probability cloud, but the other thing is that we have also measurement devices which are not clouds or detectors, right? That make clicks. That I can look whether something clicks or not. It's not a cloud, you see. So there is this probability word, which probably is some kind of Platonic nature. We don't know where are these clouds, right? We know they are not in our space and they are not real. Okay, and we have little things like detector that somehow respond to these clouds and make them sometimes jump or collapse. So we have this duality between the possibilities or probabilities and real things, that real events that we can calculate. Okay, so there is an interaction between. In this quantum fractal business, I have many detectors and one cloud. Okay, and this cloud is sensing these detectors, and at certain point, one detector click and it collapses in a certain way, and at a certain point, and then it makes some other detector click and it collapses. So it's a combination of the detectors and the cloud that is responsible for the fractality. It just when it collapses, it make a point here, it make point here, it make point here, point here, and they somehow organize because the detectors are organized in a certain way. They are like seeds around which things are being built. Okay, so you have a seed, and then you run and run and run and run and run, and the fractal depends the shape on your seeds. So that's how it works. It's not that the cloud itself produces a fractal.
So the fractals, then, I think I remember, because I looked at your book, but of course I don't know math, so
Yeah.
so I can't understand all the equations. But a lot of times I think they're depicted on spheres, right?
In this particular case, yes, I choose spheres, and the sphere is a direction of the spin, in fact. If you want to decide which direction is the spin, the direction, I put a point on the sphere. If the spin is like that, okay, I put a point.
Okay.
So it's all the jumps of the spin.
Okay.
Yes. But I have chosen spheres because it's easy to model and easy to deal with.
Mm-hmm.
Later on in this book, I went to the fourth dimension, and of course, trying to graphically represent things in 4 dimensions, it's a mess.
Mm-hmm. Well, maybe one more question related to something you just said. You said there might be a Platonic reality for where the probability cloud exists. Because I've always wondered, really, where does probability come from? Like, why does anything happen in a probability, and how can you measure that probability and have it be actually like stable to some degree? So I wonder if that's
I have a problem with, I must say I have a problem with the probability, because on one hand, I would be happy to explain all these probabilities, but by very complex behavior that we don't understand, and because we don't understand this behavior, and it's so complex, and finally we decide we can describe only about probabilities, because it's the complexity is impossible for us to describe and understand. So that's one thing, okay? I would be happy to explain everything that is we call probability, but what other people call hidden variables. There are hidden variables. We don't know about them. They do something, but because we don't know them, we don't see them. Still, somehow it happens that if we repeat experiments, we can be sure about average, what happens on average, but in this particular case, it's unpredictable because we don't know all the details. Okay, what happens? Okay, so I would be happy with this. But when I think about this, and I think about free will, I would like to have free will. In a universe that is completely deterministic and everything is determined by the past, okay, I would not have free will. If I want to have free will, at least I must admit that certain things are not determined. They are not determined, so maybe there is only probability, and I can just with my whatever thinking change the probabilities somehow, you see, and not really make something to happen, but make a probability of this happen bigger than normal, okay? And that's enough, okay, for me to, you know, so I don't really affect matter. I affect this probability cloud or whatever and make a different shape. And now what was improbable becomes more probable, right? That's, I am happy, right? So that's why I would not be very happy with deterministic universe. But on the other hand, we are thinking that past determines the future and not the other way around. But what if it's not only past determines future, but future also determines what happens now in some sense, right? How to make it work? Then the universe becomes very complicated because, you know, there are influences from the future and influences from the past. And then it can even be more complicated. You can have influences from everywhere, not only from the past, but from the future, action at a distance. And this is probably what happens, but physics is not yet there. But this is, in fact, one of the things I'm working now on, what is called teleparallelism. That is, that is the universe in which everything affects everything. It's much more difficult to understand, and it needs some math because, okay, past determines what is now. It's easy. We call it causality, right? Okay, fine. Equations. You solve equations. These are your initial data. You solve and you predict what will happen, like with the planets, right? Okay, we know the planet was here. We know the gravity field. We predict when there will be next eclipse, right? The question of solving equation. But in a universe when everything affects everything, future and past, you know, they are mixed. It's not just equation. It's something else than equation. If not equations, then what? And that's the big questions, and I would like to know the answers. That's the future of physics, I believe.
I read a philosophy book written by, well, a philosopher, but he also has worked with a physicist. And the quantum theory that they like the most is some type of decoherence theory, which I'm not going to pretend to understand, you know, exactly. But one of the ideas that stuck with me after reading this was that at a certain point in the quantum process, they argued that everything in the universe is contributing to that quantum event, but then all of the, I'll call them like irrelevant data, get I guess you could say ignored, and then only the relevant data goes into like determining the next state that thing or that quantum state will happen. Now, of course, this was the way they were describing it. There didn't seem to be any kind of math or reason for how this actually happens. It was just kind of an assumption in the explanation that somehow it does happen, that everything is affecting any little piece of the universe at any given time, but somehow most of it gets kind of like ignored as irrelevant to the thing that is actually happening. Does that idea at least tie in at all with what you mean when you say everything affects everything else?
So this, in fact, is this business of the decoherence that you mentioned, right? Is something that it's famous, it's fashionable. since like, I don't know, last 20 or so years.
Mm-hmm.
But it is something that I am very, very, very critical about. Okay. And I think it's a very bad way of doing physics, because they start with, okay, let us divide the universe into a system and environment. Well, there is a system and there is environment, and this environment is causing all kinds of noise and so on. But the question is that I am asking, and no one was able to answer me, who decide what belongs to the system and what belongs to environment? Who decide? And of course, it's the physicist who decides, okay? So for me, this is the system, and that I will call environment. This is for me relevant. This is okay. And the other physicist, no. I would add this also to the system, and the rest. And what you added to environment, no, it's not really environment. It's part of my system. And the physics in this way becomes, from the very beginning, then becomes subjective. And I believe there is an objective way of doing physics. And like when I was doing this, my way of doing quantum mechanics, where I called EEQT, even enhanced quantum theory, events were objective, and I said, we do not need an observer. There is no need an observer for the universe, for things to happen. What you need to have something that makes clicks. And whether something makes clicks or not clicks, it doesn't matter whether there is someone here or not here, you know. When the moon is there, even if no one is watching. Yeah, you don't need an observer to see the moon and, oh yes, I see the moon, so it's there, right? But if no one is watching, there is no moon. It's stupidity in mind, okay? So I wanted to do everything. The events are objective, the clicks are objective. Observer, if it is, it's good because he can make an experiment, invent an experiment, put things here and there. So it's there is a conscious mind can make experiments. But nature itself is making experiments, and things happen even before any consciousness was able. I don't think it's quite that. I think consciousness at some point necessary, because without consciousness, I don't know why the universe would have to obey any laws of why? I mean, if there is no organizing principle, no nothing, why there are any laws, right? Any regularities, but we see there are regularities, and we believe they were there even before any human being was realizing that there are regularities. So now this decoherence business starts from the very beginning, from a completely subjective division between what is system and what is environment. So I am kind of critical of it.
So if I understood you correctly, you don't think that the measurement problem has anything to do with consciousness per se. That is, when you, it's not the experimenter's consciousness, like some physicists believe, that collapses the wave function, so to speak, but it's rather something objective going on. Like you said, the measurement apparatus just does it whether you are there or not.
Yes, that's what I think, that the consciousness is not necessary to describe what happens, but consciousness is necessary in order for the world somehow be organized, except that it's not human consciousness, it's some different level of, I would say, cosmic consciousness or whatever, which which tells us what makes sense or not. I mean, we human beings, right? See, okay, there is this has a meaning for me. Meaning. There is this word meaning. Okay, I mean, in the universe without any consciousness, there would be no such thing as meaning. There would be no such things as order. Who would be there to say this is order and this is disorder, right? But there is something that tells us this is order, this is beautiful, and this is ugly. Yeah, okay. So I think at this higher level consciousness is necessary for some organizing principle is necessary. Otherwise, there would be no structure, and there is structure, I believe, but there was structure even before any human being was able to observe it. So.
And so just because I'm very interested in that particular aspect of it, couldn't it also be a combination between the human consciousness having an effect and like a higher mind keeping the whole thing stable somehow?
No, okay. What I think is that human consciousness has nothing to do with quantum experiments.
Mm-hmm.
That's first thing. They can be fully automatized and and even happen by chance, and things happen. Okay. Human consciousness may have influence on like things that happen, like paranormal phenomena, poltergeists, things. Human consciousness may have something, may be able to affect quantum probabilities. There were these experiments in one of the laboratories in Princeton. There were also German researchers doing this, whether human will or thoughts can affect random quantum phenomena. Okay, and there are there are positive results. So we somehow can sometimes influence these probabilities, I'm sure, but we are not responsible. I mean, for them to we can change their shape, right? But that's all. Things happen nevertheless, even without us. That's what I think.
Mm.
I was just wondering if you could, because you told us a bit about your career, how it started out, your school years, and then getting your PhD. But you also became a professor yourself. I was wondering if you could tell us something that you learned while as a professor. It doesn't have to necessarily be about physics, but it could be about people or about teaching. But what sticks out the most about your career as a teacher?
Well, unfortunately, as a professor, I was very much appreciated by students. My lectures, and then there were students coming to me writing to write their thesis or to do PhDs or to study under my supervision and so on. And I say it's unfortunate because one thing that happens that there was a student prize for the best teacher, and for 4 years in a row I was getting a prize from the students, right? And you can imagine my colleagues, what they were thinking. I mean, there were really movement behind my back, and then the director of the institute decided to cancel the prize for students. No, students will not because it's impossible, right? Okay, so that was that was one thing. Okay, people are very unhappy that I was collecting too many students and attracting too many students. Okay, that was one thing. Second thing, that I didn't hide my interest in paranormal and time travel and such other things that were being considered as kind of fringe interests. I was not hiding it, and I was giving talks for the large public on this subject. I was going to schools and telling students, you know, how to use computers, how to use neural networks, but I was also answering questions about telepathy and such things. So the final result of all that was that my colleague decided I am persona non grata in this institute. And after so many years, when was it? Like in '97 was my last conference. I organized a conference, Quantum Future, international conference there in Poland, and then I left and never returned. And I know now that they are still consider me as lost case, you know. He was so good, but he got interested in all this. Yeah. And it doesn't matter whether what I was publishing, that I was publishing more and better, you know, than I am lost case because I am also interested in these other things, you know. So you are lost case because you are not like them.
Mm-hmm.
Well, that happens.
Well, I think we're all glad that you're not like them. So.
Yeah, you're definitely not a lost case for us, at least. And I hope that we can have you again for more questions and actually more specific topics. And yeah, this was just to get our feedback.
You mean do some maths with you? Yes?
Yes, why not?
We have some equations.
Okay. Okay, next time.
All right, well, thank you very much. And see you next time with more questions for Ark.
All right.
Thank you.
Thank you a lot.
Thank you.